Recall in the last lecture that we looked at a 2-unit model of a 2-server system with no queue. Now what we're going to do is extend this to something that is called the hypercube queuing model, and this is for 3 servers. So now what we've got, instead of a 2-dimensional representation, which we had with the 2-unit model on the left here, now we have a 3-unit hypercube model, and this one here, both of them have no queue. So these are the simplest forms of our 2 and 3 server models here. And recall that we're using this binary server representation. So a 0, 1 means that unit 1 is busy and unit 2 is idle. So busy is going to be a 1, idle is going to be a 0. When we move to the 3-unit model, we will have, for example, 1, 0, 1 means that server 2 is idle and servers 1 and 3 are busy. And the saturated state, meaning that all 3 of our servers are busy, would be represented by 1, 1, 1. So just kind of a reminder of how that notation will work. And I'll be explaining what these numbers are here coming up. So what the hypercube applications, when might we want to use a hypercube? And by the way, this can be extended obviously past a 3-server model into an n-server model. But when we're trying to redesign police precincts and police beats, that is where people go to, or where patrol cars go, we want to make sure that, for example, if I've got a car responding to an incident in region 4, how do I assign another car, an idle car? Perhaps I have an idle car in 3. How do they respond to these different situations? And obviously the workload model matters. You know, what fraction of the time is a police person who's in 4 busy compared to 2, 1, and 3. A few years ago, I actually went to downtown Phoenix. The police were actually redesigning some of the precincts, and I believe Dr. Pan was there, and it was very interesting to see how they were going to do it, and they were considering employing some of our faculty to help them redesign that. I actually don't know how that turned out, but it was super interesting. Another possible application of a hypercube model is for, obviously, ambulances, which I talk a lot about. Same thing. How do we send certain types of ambulances to different calls? And by the way, there's different types of ambulances that you serve. There's some ambulances that serve with just basic medical equipment on the inside, and then there's some very, very high-tech ambulances. So the type of ambulance that can be sent is also can be complicated. And also, if we have non-scheduled home nursing visits, that can also be served well with a hypercube model. So the hypercube model has a lot of assumptions, and I have them here just so I can touch on them for talking points. I abbreviated them. The textbook goes into a lot more detail than I actually do here, but I've just kind of touched on the more important ones. We're going to be assuming that we can represent our geographical area in atoms. We'll just call them, like, instead of a flat surface with, neighborhoods such as, well, here, instead of showing, for example, a flat surface like this, what we're going to do with a hypercube model is we would represent this as like 4, 3, 1, and 2, and then we would connect them by their distances traveled to get to each one. So it's going to look like a network. So that's one of the assumptions that we use. Another is we're always going to be assuming that we have a Poisson process that is generating our calls for service from each one of these atoms. We're going to assume that we can get travel time data, so we'll know exactly how long it will take at whatever time of day for our unit to get to the emergency. We're going to assume that we have N, and they're called spatially distributed servers, that is response units, which means they can go to any of the geographical atoms, but we're also going to assume that they can cover other atoms as well. And that comes down here with server assignment. So we actually know where each response unit is when they're not servicing a customer, and we know it at least statistically. Then we have the server assignment. So we're only going to send one response unit to the scene of a request. If no unit is available, the request is either going to go into a queue or it's going to be lost. So the picture that I just showed you is where there's no queue, where the call is actually lost. Now, if it was really and truly an emergency, you're going to find somebody to service a fire, right? Or you're going to find somebody to go to somebody's house who's having a heart attack. But we could make some simple assumptions first where it might be lost. The next couple of assumptions are fixed preference dispatching. That means that we're going to know immediately what the primary response area is for, say, Unit 1, and when Unit 1 is busy, who their secondary choice is, and tertiary choice. We're also going to assume that our service times have a known average value, and we'll often model those as exponential service times. And we also know that service time is going to be dependent upon travel time, so we're going to include in our service time the time it takes to get to the incident, and also the time it takes to service the incident. So these are the basic assumptions of the model. Now, what does this model actually compute? And when we're talking about the model, we're going to be just exploring features of the model here. We don't have the software, or I mean, you could certainly program the software, and it's available, but we're just going to be looking at the theoretical aspects of the model here in this course. But what does the model actually compute? Well, it'll compute your mean travel time and average workload and workload imbalance. That means if we have, one response unit who's working a lot more than another, we might want to redistrict our police precincts or our response areas. We'll also have some workload, as it says, which is response unit specific. So we'll be able to identify the fraction of its calls that are in its primary response area and the fraction of calls that are outside of its primary response area. What else was I going to point out here? We'll also be able to look at these neighborhood or atom-specific mean travel times and fraction of requests and so on. So that's what the model computes. Those are what the model assumptions are. So let's take a look at an example that the textbook gives us. It is actually a neighborhood of 10 that they've broken up into 10 like sub-neighborhoods, or 10 atoms, as we said. And so what you're seeing here in the next few slides is an example only. I mean, we could come up with an infinite number of examples here. So let's see what we've got. We've got the primary area, response area for Unit 1, and I wanted to kind of color code these if possible. I don't seem to have a yellow pen here, but that's perfectly fine. We'll just use it. We'll use black, I think, or blue. Rats, sorry. I'm trying to decide here. I wish I'd brought my yellow marker. So we've got atoms 1, 2, and 4. So I could put circles around these as atoms, if you will. This is going to be my primary response area for Unit 1. So Unit 1, I'm going to color code this so you can see it a little bit better. Whenever there's a call from atoms 1, 2, or 4, we're going to send Unit 1 if Unit 1 is available. Unit 2 is going to be sent, its primary response area will be atoms 3, 5, and 6 here, right here. I'm going to color code that in green. Pretend that brown is a yellow, okay? So if I were to, you'll see this on the next slide a bit better, but so here's 2, 3, 5, and 6. And over here we're showing that my first preference is Unit 2 for atoms 3, 5, and 6. For atoms, as I said, 1, 2, and 4, I want to send Unit 1 like this. You'll see that I've color coded these on the next page right there. And then finally, we have a third unit, which is going to be responsible for atoms 7, 8, 9, and 10, which I'll do in blue here. And it will be here. So how do we read that table that I just looked at? This says, suppose I get a call in atom 8. I am going to send unit 3 if unit 3 is available. If unit 3 is already on a call, I'm going to send unit 1, whose primary response area is up here. And if units 3 and 1 are busy, I'm going to send unit 2. So you have the order of preference here, just to get you acclimated to the notation. So for example, if I needed to determine how, when I move from state 0, 1, 0 to 0, 1, 1, what does this say? This says that right now I have unit 2 is busy, and how do I go to unit 2 and 1 being busy and 3 remaining idle? Well, I would get that by having, who gets busy? Unit 1 is getting busy, so I want the rate of arrivals from region 1, because that's unit 1's primary response area, plus the rate of arrivals from region 2, whose second preference is unit 1. So let's take a look at this. If I were to look at the rate of arrivals from region 1 right here, that's going to be lambda 1 plus lambda 2 plus lambda 4. And then the rate of arrivals from region 2, whose second preference is region 1, or is unit 1, and what would that be? That would be, where are we here? So we have unit 1 getting busy because it has a call from its primary response area, and then unit 2 has unit 1 as its secondary response area. So now we also have lambda 3. You see this here? So 2 is busy already. So now we have a call from 3. I'm going to send unit 1. So we're looking at how 1 gets busy here. And same thing for node 5 and 6. 2 is busy, so I'm going to send the second desired one, right? So now we're going to have plus lambda 3 plus lambda 5 plus lambda 6 right here. I'll kind of identify these this way. And then we actually have a call from, what was I going to say? Is that right? Let me see. That is correct. That is correct. So this is how we're going to have to look at it. We're going to have to be very careful about determining how we go from one state to the next, and how unit 1 is made busy based upon the from to states that we're going to. Another thing that we're going to be using here, just some notation that you need to be aware of, is that if I sum over all of my geographic atoms, so if we were to sum I going from 1 to 10 for all of these lambdas, we're just going to call that just the general arrival rate for that particular city. Okay? All right, so that is how we're going to be reading these things. So let's take a look at the hypercube model and the values that were given in our problem in the textbook. And this is right, as I said, from the textbook. The service rates are going to be 1 service per whatever unit time. So 1 per day, 1 per hour, 1 per week, or whatever. So they've given us that each one of these servers is identical, and they'll be serving at 1, I'll just write it this way, service per whatever my time period is. So that's what all of these ones are here along this hypercube model. So let's just see how they work. Suppose that I'm in the saturated state. I have all 3 of my servers busy here. Then how do I go from 1, 1, 1 to 0, 1, 1? Well, that means that server 3 suddenly becomes idle. So server 3 becomes idle at a rate of 1 per service time. So each one of these ones you could put next to it mu equals 1. Now, same thing, let's take another look. So it's this notation you have to kind of adapt to. How would I go from 0, 1, 1 to 0, 1, 0? Well, the change here is that server 1 goes from being busy to being idle, but server 1 has the same service rate as all of the other servers, so that's why that 1 goes in this direction, and it is a 1. Now, if we had had different service rates, what if server 1 has a different, maybe it's 1.2 services per time, and maybe server 3 has a different one, then each of these ones would be specific to that server who is becoming idle. Okay, so let's take a look at the other arrows in this hypercube model here. So we've got state of server 1, state of server 2, and state of server 3 being my XYZ axis. So let's make sure we understand this. Here's my unit preference. So I've got color codes here. Atoms 1, 2, and 4 are the primary response area of unit 1 here. So we said that before, that atoms 1, 2, and 4, if you go on the previous page, we will send unit 1 if it's idle. If unit 1 is busy, atom 1 and 2, we're going to send unit 2 if unit 2 is not busy. And if 1 and 2 are busy for atoms 1 and 2, then we only have one more left, and we have unit 3. So you can see these are a little bit different. Let's go back down here to 6. If I go to atom 6 in my city, just a reminder of what that looks like. So atom 6 is right here. I'm going to send unit 2 if it's idle, but if unit 2 is busy, I'm going to send unit 1 here, and if units 1 and 2 are busy, I'm going to send 3. So we have this unit preference. So this is what we call the, in those assumptions, this is the fixed dispatch. Let me make sure I get that right. What was that called? It was called the fixed dispatch, fixed preference dispatching. Preference. So this is something you have to know ahead of time, okay? All right, now it says, so what I tried to do, and it's a little bit hard to see here, I tried to bold these lambdas, or these rates, to indicate where we had primary and then secondary service. So let's just take a look here. Here is where nobody's busy, so everybody's unoccupied, everybody's idle. So how do I go from 0, 0, 0 to 0, 0, 1? So how do I make server 1 busy? Well, the way I make server 1 busy from 0, 0, 0 is I need to get a call from either atom 1, 2, or 4. That's going to make server 1 busy. So we have lambda 1 plus lambda 2 plus lambda 4, so that's 0.75. So that's why on this arc from 0, 0, 1 to from 0, 0, 0 to 0, 0, 1, we have 0.75. Let's make server 2 busy. Well, server 2 is going to be busy from an idle state if we get a call from atoms 3, 5, or 6. So we'll add up lambda 3 plus lambda 5 plus lambda 6. So that's going to be, that will equal 0.35. And these are rates. So these are I should put it this way. It's 0.75 per whatever time I'm interested in. I haven't been very good with my units here. And similarly, I make server 3 busy by getting a call from atom 7, 8, 9, or 10, and that equals 0.40. Now let's go to some other states. How would we get out of 0, 0, 1? I've got 2 ways here, 0, 0, 1. We're going to do the third one all by ourselves here. 0, 0, 1 is, where are we here? Right here. So in going from 0, 0, 1 to 0, 1, 1, who's getting busy here? It will be unit 2, right? So how do we make unit 2 busy? Well, we can have a call from unit 2's primary response area, lambda 3, 5, 6, or we make unit 2 busy when unit 1 is busy. So unit 1 is busy here. And so I'm going to make unit 2 busy additionally by getting a call from atoms 1, 2, or 4, which is unit 1's primary response area, but unit 1 is busy, so I'm sorry, 1 or 2. So unit 1 is busy, so I'm going to send unit 2 to atoms 1 and 2. So that's what you see here. You have 2's primary and then 2's secondary response area. So that will be 0.85 per unit time here. And then how do we go from just unit 1 busy, now to unit 3 busy. Well, this is going to be unit 3's primary response area here, 7, 8, 9, and 10. And then unit 3's secondary as the secondary choice when unit 1 is busy. And so that is indicated here by atom 4 will send unit 3. So that's going to be, when you add up all of these, 0.65 per unit time. Now, what's the other way we can go? We made unit 2 busy. Here we made unit 3 busy. I guess I can't really go anywhere else, can I? Let's see here. 0, 0, 1. And so we can go to 0, 0, 0, but right now we're talking about rates out arrival. So I just want to look at the arrival rates out, because we know that the service rate, if I go from 0, 0, 1 to 0, 0, 0, then that's just going to be at a rate of 1 per time period. So here I'm just showing you how we would combine these lambdas when we move to a busier state, okay? So let's take a look at 0, 1, 0, if this makes sense. So we have 0, 1, 0, which is right here, and moving to 0, 1, 1 means we're going to make, where am I here? 0, 1, 0. I was just there. Here we go. Sorry. 0, 1, 0 to 0, 1, 1 over here. That means that I'm going to make unit 1 busy. So I'm going to have unit 1, primary response area, lambda 1, lambda 2, lambda 4. And then unit 2 is busy here. So how do I make unit 1 busy when unit 2 is busy? That means I have to have a call from 3, 5, and 6, because 1 is going to be my second choice. So that's where you have the 3, the 5, and the 6. And when I add up all of those lambdas, I get 1.1 service per unit time. And then similarly, if I go from 0, 1, 0 to 1, 1, 0, the only way I can do that by making unit 3 busy when unit 2 is busy is by getting a call from 7, 8, 9, or 10 right there. So there you go. And then I think you can probably see how this one works as well. I'm going to leave that up to you to determine where these numbers actually came from. You can hear the phone ringing in the background. I'm at my sister's house in New York State, and their landline is getting a lot of political calls today, so hopefully it's not too distracting. All right, so we have 2 more things to look at here for my rates, so you can see how they work, and then we'll end this lecture because it's a bit much sometimes. So here we go. Last 3. How do we go from 1, 1, 0, which is right here, to 1, 1, 1? Well, that means I'm just going to get a call from anywhere, okay? So I can go from 1 being idle to 1 being busy by having a call from 1's primary response area, and then just by getting a call from, well, anywhere else, okay? So here's, we've got unit 3 and unit 2 are busy, so we've got, see where all these ones show up. So we can make 1 busy this way, first choice, or 1 busy by being the second choice for unit 2 and unit 3's primary response areas. Anyways, the point is that when you've got 2 people busy and you've only got 1 more, that you can send, well, you're just going to have all of the arrival rates are going to be how you move from the to the saturated state here. So we have this per time, per time, per time. Okay. So hopefully you understand how this hypercube works. One of the things that I have done in the past, I would anticipate doing it in the future, is on quizzes and on exams, giving a blank one of these and a different one of these and asking some questions about the rates, fill in the blanks here on the hypercube. So you could probably anticipate something like that. But we'll end here for today.